This is an image of a star, a very special star, which is called a Cepheid variable. And the particular star we're looking at is called RS Puppis. It's in a southern hemisphere constellation. It's not a naked eye star, but it almost is. And so it's bright enough that you can see it through even small telescopes. And it's been observed by amateur and professional astronomers for a very long time. We have, over 100 years worth of data on the variability of this star. The star gets 5 times brighter at its peak than from its trough. So our RS Pup goes 40 or more days between peaks. That happens on a 41-day timescale. Brightness from its dimmest to its brightest is about 5 times brighter. So that's a huge change. It's about 6,500 light years from Earth, and that's a really important number for us to know. The distance, the precise distance. It turns out it's a really important benchmark in how we understand the scale of the universe. Cepheid variables have a very special relationship between the period of variability, how fast it goes from one peak to the next, and their absolute brightness. So how much energy is coming out of that star. And if we know something's relative brightness, and we can measure its absolute brightness from something like the period luminosity relationship of the Cepheid variable, then we can tell you what distance it must be at to look as bright as it looks to us. So this is a Cepheid variable. They're very important in our history of understanding our scale of the universe and how it evolves. And this particular Cepheid variable is in our galaxy, so it's nearby enough that we can study it really well. This one is so special because it's near the tip of that period luminosity relation, so it really allows us to calibrate the entire relation. And the fact that it's embedded in this beautiful cloud of dust, it looks amazing, the stunning Hubble image with all the filamentary details. But there's also science embedded in this light. And that science allows us to get an extremely accurate distance to this Cepheid variable within about 10% accuracy or even better. But this is a star that's about 10 times more massive than the Sun. More massive stars, they live fast and they die young. And when that happens, the star starts to go through these changes. And so that's what is actually driving the period luminosity relation, is that the star is actually unstable during this time. And when it's got a lot of heat coming from the core, that core has to do something when it expands. The radius gets much bigger, the star gets brighter, to a certain point where it cools down, and that starts to contract again. Now it doesn't have as much energy, it starts to fall back into gravity, where it gets close enough that it heats up again. That's actually what's driving these period luminosity relations. So even though this star is younger than our Sun, because it's 10 times brighter, it's actually more evolved. When you first look at it, it almost looks like the material itself is spewing away from the star. But that's actually not what's happening. What's happening is that the light takes to get to the further out dust and gas is longer. So we're basically looking at almost like a snapshot through that gas and dust reacting to the light. And that light echo allows us to make this extremely precise distance measurement. Now, due to improvements in our measurements of Cepheid variables like RS Pup, we have now really narrowed down that window, like what is the age of the universe. We now know it's 13+ billion years old. And we've seen that it's not just expanding linearly, but it's actually an accelerating universe. It's all intimately tied to our understanding of Cepheid variables, and this one is the best studied.